Okay guys, so yesterday I talked about the 68%, 95%, 99.7% of the data is within those 1, 2, 3 standard deviations from the mean. So we're going to keep talking about that today, do some more examples, and then I'm going to introduce a new word to you called Z-scores or Z-scores, depending on how you like to say that letter. So let's review what we did last day. So a nurse records the number of hours an infant sleeps during a day. He then records the data on a normal distribution curve shown below. The values shown on the horizontal axis differ by 1 standard deviation. So again, because 12 is in the middle, we know that 12 hours of sleep is the mean, because that's the one that's in the middle. We can see what the standard deviation is because we can look at what it counts by. So we see there that they added 2 and minus 2, so that means that 2 hours is our standard deviation. Okay, so then how many hours sleep does 68% of the babies get? So remember, 68% is 1 jump, so that means it's between 10 hours and 14 hours of sleep. What percent of babies sleep between 8 and 16 hours? So we have to continue our axis here. So if we're going to be adding 2 hours, we're going to go adding, and then if we minus 2 hours, that would be 8 and 6. So continue with this question now. What percent of babies sleep between 8 and 16 hours? So 8 and 16 hours is 2 standard deviations or 2 jumps away from the mean in each direction. So that would be the 95%. So 95% of babies should be sleeping between 8 and 16 hours. So that's a big spread, right? That's the problem with some of this data is there's a big difference between sleeping 8 hours a day versus sleeping 16 hours a day. So when somebody says, your child is sleeping the normal amount, so notice the word normal. We tend to think of normal as regular, but actually mathematicians, when you hear the word normal, we actually think of bell curves. So because a bell curve has so much space on it, to say 95% of babies sleep between 8 and 16 hours, it's almost a useless statement, right? It has to be, the standard deviation actually needs to be quite a lot lower in order for the data to mean something, because high standard deviation graphs really don't say a whole lot, because all you have to do is go 2 jumps out and you get this huge range of values. So it kind of loses its meaning. So there are 2 ways we can talk about 16 hours of sleep. So if you remember the 16 hours, okay, so the 12 was right here. The 16 hours was 2 jumps above the standard, 2 standard deviations above the mean. So we can either say that 16 can be represented as the mean plus 2 standard deviations above the mean. So that's one way we can explain, give it a notation. The other way is to say 16 has a Z-score of positive 2.00. Now all this is showing, this is just, a Z-score just says where it is in relation to the mean. So because 16 was 2 jumps above the mean, then we say it has a Z-score of 2.00. And we always take it to 2 decimal places. Always. Okay? So what would it be for 10 hours of sleep? So remember again, 12 was here in the middle. So 10 was right here. So 10 was 1 jump below. So for 10 hours, we would say the mean minus 1 standard deviation. Or, since it is 1 jump below, the Z-score is negative 1.00. Because it's 1 jump below the x-axis, whereas 16 was 2 jumps above. So what would the Z-score for the mean be? Well, if we think of it like this, and just kind of use our reasoning here. So 16 was plus 2. 10 was negative 1. What number do you think goes here? 0. So the mean always has a Z-score of 0. Because if you think about it, Z-score is how many jumps you are away from the mean. So if you're on the mean, you're 0 jumps away from the mean. So the Z-score is 0. So then what we can do with our normal distribution is we can change our picture. So this is written what I refer to as like an x-axis or with data values. So we've got 10, 12, 14, 16, 18, and then 8 and 6. So that is written with the data values of adding the standard deviation to and from the mean or subtracting. If we want to write that in z-scores, it looks like this. So positive 1, 2, 3, negative 1, 2, 3, 0, 0. Now, every normal distribution will have that as the z-score. So the data values change for every question, but the z-scores never do. Because remember, the z-scores are just showing the number of jumps you are away from the mean. So we go 3 jumps up, 3 jumps down. So here, 18 would have a z-score of 3. 8 would have a z-score of negative 2. Okay? So, z-scores can be used to compare data with different normally distributed data. So where this comes in handy is when we want to compare data. So let's say a nurse in Canada was looking at the sleeping patterns of infants, but a nurse in Mexico was also doing it. So let's say they ended up with a different mean and different standard deviations. So they would have different x-axis numbers for each of their data sets, but if we convert all of their data to z-scores, because every z-score graph looks the same, again, negative 3 to positive 3, because all of it gets converted the same way, it makes it a lot better and a lot easier for us to compare data. That's why we have z-scores. So, by comparing data values to a mean value of 0, it becomes very easy to compare and contrast all data values. Okay? So, let's look at an example here. So, a z-score indicates the number of standard deviations that a data value lies from the mean, or another number of jumps away. So this is a formula that we use. You don't have to have it memorized. I will give it to you. So we use this formula to compare data values. Okay, so x is your data value. This is your mean. This is your standard deviation. Okay, if you end up with a positive z-score, that means you're above the mean. If you end up with a negative z-score, that means you're below the mean. Okay, so let's look at an example. This should start making sense here once you see an example. So I'm just going to skip this one. I will come back to it here. I just want to do an actual example with you that might kind of solidify this in your head. So in math class, Meg has a mark of 91. Okay, so I'm just going to read just this part of the question. So in math, she's at a 91. In English, she's at a 93. So if your parents are looking at your report card, they're thinking you're doing better in English than you are in math because you got a higher mark. But here's the difference though. The class average in math is 74. The class average in English is 77. Do you understand what I'm doing here? So even though she's got a 91 in math and a 93 in English, if you look at the class average, everybody in English is doing better than everybody in math because the class average is higher. So now it's like, is she really doing better in English as compared to her classmates? So this is where z-scores come in, because what it allows us to do, instead of comparing 93 to 91, we're going to look at how many jumps she is above the mean in each case, because she is above the mean in both ones, right? Here she's at a 91, class average is 74. English is 93 with a class average of 77. So she is above the class average, but let's see how far above. So for math, her z-score, so her mark is 91. Class average is 74, and standard deviation is 5.4. So if you're going to plug this into your calculator in one step, make sure that you put brackets around the numerator, and then round it always to 2 decimal places. So we're going to go 91 minus 74 divided by 5.4, and we get out 3.15. So in terms of this, she's actually an outlier. 1, 2, 3. So again, she's actually right here. She's well above the class average in math. Okay, now let's look at where she does in English. So in English, remember, she was at a 93. but the class average was a 77, and the standard deviation was 6.8. So also knows the standard deviation. It's lower in math than it is in English. So that means her data, everybody is closer to the class average in math, whereas there is a little bit more spread out in the English class. So again, 93 minus 77 divided by 6.8. So 2.35 is her Z-score in English. So in English, so again, if we make this a 0 for the average, 1, 2, 3, she is actually right here in English. So in math, she's 3.15 jumps above the mean. In English, she's only 2.35 jumps above the mean. So she's actually doing better in math as compared to her classmates. Okay, so again, it's in comparison to the average. So when your parents look at your report card, or when you're looking at your report card, it's not so much necessarily what your mark is. I mean, yes, that's important, but it's also how it compares to how everybody else. And unfortunately, that actually doesn't get reported on report cards. That's why when you're asking, hey, how did the class do? What you're doing in your head is you're comparing yourself to everybody else without knowing everybody else's marks. Okay? So it's a very useful tool, actually. Now, where comparisons are really important is actually, one uses on IQ scores. Another one is actually with babies. I'm sure if you've had like younger brothers or sisters or nieces or nephews, when they are growing, when they're babies, and they go in for, let's say, their 2-month checkup, the doctor will tell you actually where they're at based on normal curve. They'll say, you know what, they're in the 75th percentile. What that means, 75th percentile, it means that 75% of children are, let's say they're doing it with the weight. So 75% of children weigh less than your baby, and 25% of children weigh more than your baby. So if your baby is on the 50th percentile, it means half the amount of babies weigh more than your baby and half the amount of babies weigh less than your baby. Okay? If your child is in the 20th percentile, it means that 20% of babies weigh less than your baby, 80% of babies weigh more than your baby. Okay? But again, it's in comparison in relation to others. Okay? But as long as you're on that curve, okay, so as long as your percentile is somewhere between that 20% and 80%, usually everything's just fine. But also because kids go through growth spurts, maybe you just happen to have your appointment before they suddenly shot up. Because again, once a child gets taller, their weight kind of gets in line with their height. So they may change percentile rankings very, very quickly. Okay? IQ tests are another way we rank people in relation to everybody else. So IQ tests are sometimes used to measure a person's intellectual capacity at a particular time. IQ scores are normally distributed with a mean of 100, so a mean of 100, and a standard deviation of 15. So we're going to add 15, and we're going to minus 15. Okay? If a person scores 119, so 119 is right there, how does this compare with the scores of the general population? So right now, we can actually estimate their Z-score. So right now, 115 would have a Z-score of 1, 130 would have a Z-score of 2. So 119 is going to have a Z-score somewhere between 1 and 2. So I'm going to estimate 1.35, just as an estimate. Okay? To figure out exactly where they rank, we would have to use our Z-score formula. So we're going to go 119 minus 100 divided by 15. So what is their Z-score? Their Z-score is 1.27. Okay, so that was a pretty good estimate, but this is the actual. Okay, so they are 1.27 standard deviations above the mean. Okay, now what does that mean for percent? Well, we don't know that right now. Remember, this is 50% right here. This is 34. And this whole column is 13.5. But remember, I'm right here. So maybe it's half of it. So let's say maybe it's 7. So if I go 50 plus 34 plus 7, that would be, let's see here, 84 plus 7, that would be 91. That's an estimate. So let's say that's another way you could do it. You could say you have a Z-score of 1.27, or you could say you're 91%. So in other words, you're brighter, you scored higher than 91% of the population. Or another way you could say it is only 9% of the population scored higher than you. Okay? So you can use the percents or you can use the Z-scores. But that's just two different ways that you can interpret the data, which is what we're trying to do here in Math 20-2. Okay? So that concludes this lesson. Let's try the handouts, see how you do on it, and if you have any questions, don't be afraid to ask. See you in the next one.